Hello, everyone. My name is Chris Myers. I'm in the Cornell Center for Advanced Computing, and I'm going to be talking to you today about scientific computing with Python. And this is part of our scientific computing training series. And my colleague, Christopher Cameron, will be assisting with answering questions in the chat during this. So we're here in a Jupyter notebook, which is running Python. I'm going to start with sort of providing just a quick overview of the Python software ecosystem for scientific computing and data science. And most of the lecture will sort of focus on a few core packages that are widely used for a lot of different kinds of application areas. And then I'll sort of try to wrap up by talking a little bit about how those packages fit into this larger ecosystem. And then finally, there'll be these hands-on exercises at the end of the notebook that we can work through some of. Just in terms of additional resources, we've given a couple previous lectures in this series. You might want to revisit both the slide decks or the recordings. The Python website has lots of useful documentation about the language and the standard library. And then each of these packages that we'll be talking about has their own documentation that's quite extensive. We also, as part of in the CAC, produce a number of online training materials in the Cornell Virtual Workshop, and there are many topics in there, but I've just listed a few here that would be relevant for this subject area we're talking about today. So just in terms of some logistics working in this notebook, so as I said, we've scheduled this as a 90-minute session with a hands-on component. And if you want to run the exercises in the notebook, then you can go to this site and get further information. You'll either need to run the software on your local machine or in some sort of cloud environment that supports Jupyter or Jupyter Lab, and such as some of those that I've listed here, and I'll show you very briefly. And then there'll be a number of additional packages that you would have to have in whatever environment you have in order to run everything in the notebook here. So I'll proceed through this notebook throughout the lecture, and I'll execute code cells. And if you have the notebook and have the software installed, you can sort of follow along and do that. And as I said, I've saved most of the exercises for the end of the webinar, where we can kind of work through them and talk about solutions. And then solutions to all the exercises are at the very end of the notebook, so you'll have that as reference. I did mention that there are these other environments such as Amazon SageMaker. So I have, for example, this Amazon SageMaker Studio Lab set up where I've got my notebook loaded in there. I'm going to be running it off of my local Python installation. But if you wanted, you could go, for example, to Git and clone. And we have this instructions in the README, clone the Git repository that this notebook is in, and then you could load it up into SageMaker Studio Lab. Or you could go to Google Collaboratory, which provides a kind of different interface. But you could go, for example, to here and upload the notebook once you get it from the GitHub repo, and then load it in and run it there if that's of interest to you. We do have a quick poll question that I guess I will launch here. So please, this is just trying to get a sense of to what extent do people plan to participate in the exercise component of this at the end. If you could just quickly select one of these options here, that would be great. And I guess I can just kind of leave the poll open there and continue, right? Because I think I could do that. Right. For those of you who've been to the two previous talks in the series, you'll know that we had fire alarms both times, right at about the same time, at about 9:22 a.m. We're hoping that doesn't happen again. But if we do suffer through yet another fire alarm and I need to exit the building, Christopher, fortunately, is not in Rhodes Hall this morning, so he can help lead the way while I'm evacuating. And a good place to start might be, for example, to go to the exercise at the end and start trying to connect there. So here's a first simple exercise. What number results from adding 2 and 4 and raising the sum to the 6th power? So everything I've shown you up to now has been marked down documentation, but of course in a notebook we have live code cells. And so I can execute this. I can type in 2 + 4 and then raise that to the 6th power. Python as a calculator is a great tool to use, and I encourage you to explore that. You could also, for example, if you're running this try to figure out whether you have all the packages you need, all these ones that I listed. And so, for example, I can execute this code cell, and it'll try doing all these imports. And if any of them are not found, it'll complain, but I have them all here. On the SageMaker Studio lab, I did discover that if you run with this, if you choose this SageMaker, it's SageMaker distribution :Python kernel is actually the name of it, but that doesn't have these two packages in it, stats models and OpenPyXL. So if you're running on that system, you could, for example, go to this code cell, uncomment the last line with this conda install, and that should install those packages for you on your SageMaker Studio lab instance. And Christopher talked about that a little bit during his last talk when he was talking about a Jupyter lab in the cloud. Again, if you have questions, in the chat, we're paying attention to those, and I think, let's see, how many people? 24 of 29 participants. So I guess I can end the poll, or I can leave the poll going. I don't quite know, but I'll leave it going, whatever. So I just want to start. So Python at its core is a programming language, and I talked more about that during my last lecture 4 weeks ago in the introduction to Python. But just to sort of reiterate a few points relevant for this lecture, Python is a general purpose programming language. It wasn't developed specifically to support scientific computing, unlike many other languages you might have had some experience with. And it's also not a compiled language, it's an interpreted language, although there are opportunities for compiling parts of Python. So it's interpreted, which allows for sort of rapid development time, but potentially slower execution times. But at the same time, Python is an extensible programming language. And what that means is that we can actually, within the Python interpreter, which is actually written in the C programming language, there's an API that allows us to link Python code to compiled code in C or other languages. And in fact, this allows us to develop what are called extension modules that are compiled chunks of code that we can call from Python, but that are typically much faster than the pure interpreted Python. So most of the functionality for scientific computing and data science is provided by third-party libraries which are often implemented using these kinds of compiled extension modules to support numerically intensive computing. And the scientific computing community has been an important participant in Python since its early days. So I have this picture here, and you may have seen versions of this in some of the previous talks. Again, at the root, we have Python and this API that lets Python talk to other languages. I'll be talking a lot about NumPy today, which is really a kind of a foundational package that uses this API, sits on top of Python. I'll also be talking about SciPy and Pandas and matplotlib, but really, these are just a few foundational components in what is a very large ecosystem of lots of different packages that support a lot of different types of application areas. I've got a few pieces of information here. I went through this in more detail during my last talk, so I don't necessarily want to go through this all now, but I mean, essentially, because we need these third-party packages when we're running Python for scientific computing, we need to think about how to install those. We can create environments, virtual environments, and use various package managers. And rather than having, say, one big Python installation that's got everything we might ever possibly need, it's generally better to try to create smaller focused environments that sort of support whatever particular problem areas you're working with. So if you have a Conda-based installation from Anaconda, Conda is a package manager you can use. And so, for example, I created, and I'm running this notebook, in a Conda environment that I created called PySciComp, which has these packages in it that I need, and then I can activate that and run that. If I were running in a non-Conda based environment, I could use the Python VENV module to create a Python virtual environment, and it would be a similar kind of thing. I could create a Python environment and then use the pip package manager to install whatever packages I need. I'm going to sort of, having left that kind of logistical stuff there, having kind of laid that out, I want to now sort of dive into some of the components of this ecosystem that we use for scientific computing. And I'll just take a sip of tea here. So I want to start talking about NumPy. We have a question here: is VS Code Conda based or non-Conda, or is it an entirely different thing? So VS Code is an IDE, an integrated development environment that allows you to program in Python. It would support, I mean, it would support whatever kind of, I think it would support whatever kind of package management you want to use. I mean, it sort of depends on how you have have Python installed, but it would support either Conda or sort of pip-based kinds of packages. Okay, there's so we can continue to talk about some of these kinds of questions, but NumPy is this package. It's short for numerical Python, and as I say, it's really sort of the cornerstone of this scientific computing ecosystem. It's largely written in C, which is a compiled language, and it's got links to packages for supporting linear algebra. And so it's more performant than sort of the pure Python code we might run, because it can execute code in compiled language, in this compiled language, and we'll look at that in a little bit more detail. And one of the key data structures that really the key data structure that NumPy provides are multi-dimensional arrays, which are described here. So this is really sort of the core data structure provided by NumPy, an ND array or an n-dimensional array, and this kind of generalizes to some extent the notion of a Python list, which is a one-dimensional thing, but which can have sort of nesting in it. But NumPy arrays are inherently can work in arbitrary dimensions, and it provides not just these data structures, but also a very powerful array syntax that enables both compact expressions and efficient computations, and it really sort of plays an important role throughout the ecosystem. So in a NumPy array, we've got some we have some number of dimensions, and this is a 2D array, and the axes of an array describe the ordering of the indexing. So rows are indexed along axis equals 0, which would be the first index position, and columns axis equal 1. And then there's a shape of an array. So this is a shape. This array that I'm showing here has a shape 8, 3. It's got 8 rows and 3 columns, and it's got a type associated with it. In this array I'm showing on the left, the D type, as it's called, is an int, but we can have floats or complex numbers in arrays. And of course, if we have higher dimensional arrays, say a 3-dimensional array, then we would just kind of extend this indexing to however many dimensions we'd have. So there would be an axis equal 2 in a 3D array. So there's lots of facilities for say creating arrays. So I can import NumPy, and conventionally we say import NumPy as NP. And one way of creating an array is to explicitly create it from some data. So this is a Python list of lists, and it then it produces this 2-dimensional array X that I assign here. And I can, for example, ask what is the shape of that array, and the shape is this tuple 4, 3, because it's got 4 rows and 3 columns. There are other ways of creating arrays. I can create random arrays of a given shape. So I can create an array of uniform random numbers between 0 and 1 with shape 4, 3, and that gets produced there. But of course, if I run that a second time, I will get a different array because it's random. And then there are ways of creating, for example, evenly spaced arrays. If I want to create an evenly spaced array such as this, I can use this linspace function. So as I said, NumPy arrays are kind of multi-dimensional generalizations of Python lists, and so they extend both the list indexing and slicing syntax to multiple dimensions. So indexing, I can either index to access individual elements, and the counting starts at 0, is 0 based, and negative indices actually can count back from the end of an array, as we'll see. And then slicing, which uses a colon syntax, allows us to access ranges of elements. So if for example, I create this array A, which now has shape 5, 4, I can access an element of that A1, 2 And that gives me the element in the first row, which I'm starting at 0. So the first row is what you would think of as the second row. Row 1 is the second row, and column 2 is the third column. And so that gives me that entry 7. I can, for example, ask for an entire row just by providing one of the indices, and that returns this entire row 1. I can slice using this colon syntax and just slice out, for example, this little upper left corner of the array from 0 to 2. So it gives me 0 and 1. It does not, the upper bound on the slice is not included. If I leave off bounds on this slicing notation, it basically slices, say, to the end of the array. So if I use this notation 1 colon comma 2 colon, then essentially what it does is it extracts out this lower right-hand portion starting at those indices. So this is a very powerful syntax. If I leave off all the bounds, I basically get everything along a given dimension. So if I want the first 2 rows of this array, I can access it with this kind of thing. Or if I want, for example, an entire column, I can loop over all the rows and ask for column 2, and then I get back what's in column 2. Although it's as a 1D array, not as a column vector, which is something that you might see differently in something like MATLAB. And then, as I said, we can access things with negative indices, which basically work back from the back of the array. So here was my array A, and if I use this notation, I'm basically asking for the last 2 columns, which are those 2 there. And so this is this negative indexing is very useful, especially when you want something from the end of an array, but you don't necessarily want to have to figure out how big the array is. You can just say, I want to count from the end, however big it is, rather than, for example, figuring out, computing the length of the array and then working with that. So here's a little exercise. We want to create a random 6x6 array, and then we want to set all of the external boundary elements to 0. And this kind of thing might show up if you were using an array to represent a field, and there were some boundary conditions on that field that you needed to set. So let's think about how we want to do that. What I was showing you here was ways of accessing elements, but we can actually use the same slicing syntax to set array elements. And I've kind of hidden the answer here, but we'll just do this. How do I unhide this? There we go. So the way that we would solve this exercise, for example, is that we've already seen this random number generation syntax. So I want to create in this case, a 6x6 array of uniform random floats between 0 and 1. But then I can assign to slices values. So for example, what this thing does here is it says along every row on the 0th column, I want to set that to 0. So that sets this 0 column here to 0. And I can do that using the slicing syntax to set each of these four boundaries. I realize I didn't give you much of a chance to work on that exercise, but I did want to at least give you a chance to think about it momentarily. So this would be one way of doing that. Of course, then if I run that, I'm going to get an answer, although it's going to be a different answer that's in my example here because it's random. And this array indexing syntax, of course, extends to arbitrary dimensions. So if I have a 3-dimensional array of shape 3, 4, 2, which is sort of just depicted here, then I can, for example, slice out the back end of that, essentially the last, the last entry, the last plane of that 3-dimensional array in the on axis equal 2, and essentially get these elements that are in that back row. So the syntax is very powerful and very general, and I've just kind of shown you the sort of the beginnings of that. There are a number of array operations. We can act on arrays in kind of with unary operations in kind of an element-wise fashion. So I've listed a few of those here, and these would then produce a new array of the same shape, but where each element is transformed by whatever operation I've specified. There are element-wise binary operations if I want to add to arrays or subtract them, or even sort of do logical comparisons. and we'll look at some of these. There is, of course, support for doing matrix multiplication and dot products, as would arise in linear algebra. There's a variety of aggregating operations and various ways of manipulating arrays. So, for example, I created above two arrays X and Y that have the same shape. And so I can, for example, multiply every element in X by 3 and every element in Y by 4, and then subtract the one from the other, and I get this new array W. I could ask, for example, where is W, but I can create a Boolean array, which is false wherever W is not greater than 10 and true wherever W is greater than 10. And so this now produces a new array, which is of the same shape, but contains these Boolean values that are often useful. I can, for example, use that as part of this np.where. So what this says is, wherever W is greater than 10, give me W, otherwise give me 0. And I wouldn't necessarily need to give a value here. I could actually have a different array. I could say wherever W is greater than 10, give me W, otherwise give me some other array at those same elements. And so this is a very useful kind of syntax, and there's a lot of similar kind of functionality within NumPy that lets us act on arrays in various ways. I mentioned that we can do things like element-wise array addition. So, for example, I can create 2 1,000 by 1,000 random arrays and run them, and it then with this line C equals A plus B does an element-wise addition of all of the elements in those those arrays. And in fact, we can, within this notebook, we can time that. So this time it magic function will run this thing several times, and it tells us that it takes approximately 921 microseconds to do that computation there, right? And sort of the analogous thing that if I weren't using this array syntax, this compact notation to add to arrays, would look something like this. I would first have to check that A and B are the same shape, and then I would have to sort of pre-fill some resulting array with zeros, and then I would loop over all of the I and J indices on that two-dimensional array and build up element by element wise a result. And if I time that, it turns out that this takes 252 milliseconds per computation, per solution there. And so we can ask, for example, what is the speed up? That would be 252 milliseconds divided by 921 microseconds. And so that's a speed up of approximately 273 by using this array operation, as opposed to sort of doing this explicit looping in Python and doing the addition one element at a time. And so you might not care about differences between milliseconds and microseconds, but if you're doing this millions or billions of times, you might care, or if you're working with very larger arrays. And the reason that this is so much faster and is sort of depicted in this diagram here is that when we loop over this array in Python, the indices I and J, and then add up elements one at a time, basically every time through this loop, we're diving down from the Python interpreter into this compiled extension module, which is NumPy, and we're accessing elements, we're adding them, and then returning a result back to the interpreter. And that takes a long time. It's a lot of overhead, sort of jump back and forth between these different layers. Whereas when we just execute this command C equals A plus B, we basically make one call into the extension module, into NumPy. We do all the looping and indexing and addition in there, and then return a result. And that ends up being, for this example, 273 times faster. So, so these array operations represent a form of vectorization. They can be ported to other backends that support vectorization, such as GPUs. The conventional wisdom is that, again, you should avoid these kind of looping operations in Python if you can do so and use this array syntax for better performance. But one of the challenges is figuring out how to express more complicated operations solely using the array syntax. Obviously, this array addition example is simple syntax, but in other cases, you might need to think about how to manipulate the data to without having to resort to for loops. One caveat here is that this array syntax, while it's very convenient and compact, can disguise some performance inefficiencies if you have long expressions you're evaluating, there might be a lot of temporary arrays that get created, and that's something to pay attention to. And there are, in fact, are alternative approaches that actually use compilers to generate more efficient code. If you were to sort of unroll this, these loops like this and then run it through some of these compilers, you can actually get better performance than with NumPy. But that's something we've talked about in our CVW. So there are various aggregating operations we can do. If I have some array X, I can, for example, compute the sum of all the elements in the array, and that's shown here. But maybe I want to do it as kind of a sum over the rows. So that would be, I could do a sum, but I would specify an axis. I'm going to do a sum over axis equals 0, or I can do a sum over axis equal 1, the sum over the columns. I can compute the mean over each row, or say the standard deviation over each column. And so these aggregating operations can be done along different axes. And again, that often plays an important role in some kind of computation you want to do. So that was a very quick breeze through NumPy, and I've only showed you a few features. There are many more. There's all sorts, again, if you're doing linear algebra, there's support for all sorts of different kinds of matrix operations and the like. There are lots of these exotic array broadcasting operations that enable you to sort of work with arrays of different shapes in different ways, and then lots of functions to filter or process data. And we'll revisit some NumPy arrays in the exercises at the end. So I'm going to move on now to talking about SciPy, which is short for Scientific Python, and this is a big set of functions and tools that sit on top of NumPy, and in fact wrap many sort of well-developed and well-optimized C and Fortran numerical routines, but provide convenient and consistent Python interfaces. And as sort of described in this table here, there are sub-packages that support a number of different kinds of operations. And these are kind of, each of these is kind of a high-level sub-package, which then has a lot of different functions embedded within it. And we're just going to look at two of those sub-packages to integrate and optimize ones, but depending on what kind of work you want to do, you might want to explore some of these other tools in SciPy. So as an example, I'm just going to look at a kind of a simple differential equation model for infectious disease dynamics, similar to many that you may have seen during the pandemic. This is an SIRS infection model, which means that I have susceptible hosts who can become infected, infected hosts who can infect others, and then recovered hosts that do not get infected. And then there's a set of state transitions of infection and recovery, and in this case, a waning immunity. And without going through all the math of that modeling, we get a set of differential equations that describe the time rate of change of the S, the I, and the R components of this model. And so as written, this sort of typically appears as kind of an initial value problem, in the sense that we started some initial conditions, some initial values for S, I, and R, and then we want to integrate this differential equation forward in time to see what the dynamics looks like. And most packages, including SciPy, provide some sort of, or most languages provide some sort of package that allow you to do this kind of integration of differential equations. And they typically all require that we write a set of differential equations in this form. So we have some vector of state variables y, and then we have a right-hand side that describes how each of those state variables changes in time. So we have some independent variable time and some vector of state variables and some parameters that determine what that dynamics looks like. And then we have this function f, which is this essentially the right-hand side, the instantaneous rate of change of the state variables. So for this SIRS model that I'm showing you, the state variables are the S, I, and R fractions of the population that are in each of those states. We have these parameters that I didn't really talk about, but we have parameters beta, gamma, and rho that describe various the rates of different transitions in the model. And then this function f is essentially just the three components of the right-hand side of those differential equations that I showed above here. So we can write code, for example, essentially to run this, what we need to do is that we need to use the solve IVP, so initial value problem. We want to solve an initial value problem using this function from the SciPy.integrate package. We can define some parameter values, but the key thing here is that we need to define this function f, which I'm calling here SIRS. So this is basically just returning a three-component vector for the time rate of change of the S, the I, and the R components. And then essentially I can, once I've defined that, I can integrate that function starting from some initial condition, why not, for given values of parameters over some time interval. And if I do that, you should run, and I get some output, and we can look at what this output tells us. What this output tells us is it's got the times that it's returning a solution on, and then the values of these state variables, each of the three state variables over each of those time points. It tells us, for example, that it evaluated this right-hand side function 116 times during that integration. So it repeatedly took lots of small time steps. It was actually doing some adaptive time stepping, and called this function repeatedly in order to be able to integrate that differential equation by discretizing in time. And then once we have this solution, we might want to see what this thing looks like. And so we can use, for example, matplotlib, which I mentioned before, which is sort of this one of the central plotting packages in Python, really probably the central plotting package. And I can, for example, plot the dynamics of each of these three components, of the S, the I, and the R components. I start with an initially susceptible population. I have some small amount of infection. I get some infection that runs through the system, and eventually it kind of settles out to some steady state value, which is non-zero. So in this SIRS model, the infection is actually endemic in the population. It'll settle down. There'll be some initial bump for these parameter values, but then it kind of settles to some steady state value. If I were to go back up to here, for example, and change this row parameter, row is the rate at which a recovered host becomes susceptible again, and I were to rerun this, I would essentially now have an SIR model, and we'd see that I would have a little wave of infection that runs through the system, but eventually the infection dies out. And this is characteristic of SIR models, is they don't support endemic infection. They just they eventually burn out as the infection dies out. But let me get rid of this because I want to have those things for later. So that's my endemic state. Again, depending on parameter values, I can get different qualitatively different kinds of dynamics. Another very useful thing to do in SciPy is, for example, being able to estimate parameters by fitting a model to data. And so, for example, with this set of differential equations, for every set of parameters P, I get some trajectory of the three state variables over time. And I might, for example, want to find the best set of values of P that fit some data. I might have data on infection levels. And so I could, for example, define a least squares cost function that describes how my trajectories for any given parameter value P deviate from whatever data I have. And so I can, for example, just generate some synthetic data. I generated some noisy data that look a little bit like some of those infection waves we had. And then I essentially want to be able to try to find an optimal set of parameters that minimizes this cost function. This is a typical kind of optimization problem where we have some objective function, some cost function, maybe we call it a loss function, that we want to minimize, and we want to find the set of parameters that minimizes that set. And so we can do that in SciPy using this minimize function from the SciPy.optimize subpackage. We define this cost for any value of the parameters P. I need to integrate my differential equations and get a solution, and then I need to compute this sum of squared errors, the deviation of the solution at each of those time points from the data. And then I constructed this so that I just sort of have daily infection data, and I'm computing the solution on a daily time scale. And then I typically need to provide some initial guess for the parameters. So I'm just going to make some initial guess for what the values of beta, gamma, and rho are. But then when I pass all of that to an optimizer, in this case using this Nelder-Mead method, which does kind of a simplex optimization, I get a solution where I see here that and in fact, did it print my p-opt? I don't see that there. Oh no, this is the p-opt, right. And so it actually evaluated this cost function 274 times for different guesses of parameters, and provided some a guess, sort of this is the p-opt. This is the optimal set of parameters that best fits the data. And so now we can go and we can, for example, plot this. We can plot the data that we were trying to fit to. We can plot the initial guess. So that initial bad guess of parameters did a poor job of fitting the data, but then by optimizing, by minimizing this cost function, by iterating over different parameter values, it found a set of parameters that does a much better job of fitting that data. And this is a typical sort of example of kind of nonlinear parameter estimation using a tool like this. And in fact, one of the exercises does something similar with a different kind of data set. So I hope I've just given you a quick sense of some of the kinds of things that SciPy provides support for. Again, by abstracting these common operations of things like integration or optimization, we can basically write conveniently in Python functions that sort of specify the details of whatever problem we're working with, and then use the tools in the package in order to address those things. I think I'm going to go over here and end the poll just so that in fact is there. And I see that there's been some discussion here. It's more about some logistics of working with R and things. Okay. So I'm going to move on now to another important package in this ecosystem, which you may have some experience with, which is Pandas. And Pandas is very useful for dealing with tabular data, with data that you might, for example, get in a spreadsheet, such as depicted here. So as opposed to a NumPy array, which is sort of an n-dimensional thing which has all the same type, in these kind of data tables, we often have columns that are linked to each other, but they may have different data types. So if we have a series of observations of temperature and rainfall observations by different people, we might have a spreadsheet or a CSV file that sort of accounts for each of these observations. But each column then is a different data type, but we want to be able to reason about those all together. And so Pandas defines these data frames and series objects that allow us to deal with these kind of tabular data, and in fact uses NumPy underneath to store this data and to do much of the data processing. So Pandas provides support for reading from CSV and Excel files and SQL databases and other sources, and then it provides a lot of useful functionality for working with this kind of data that I'll show you a little bit of. So here's an example of let me down here. Here's some data on baseball statistics. So if you go to our CSV on Python for Data Science, I do lots of stuff with baseball statistics. So if you're into that, you can go visit there. This is just one of the data tables that's provided by this organization called the Baseball Data Bank. This is the history of batting, of hitting statistics in Major League Baseball, dating back to 1871, and I ran this through the end of the 2022 season. So what this batting table is, every row is a player and a year, and then a set of statistics for that player in that year. And so this is stored in a CSV file. I was able to read that, and then I get this data frame, which kind of organizes all that information. And then I can, for example, ask for summary information about that, and it tells me about how many different entries there are and things like that. So one of the nice things about Pandas is you can add derived data by indexing, or you can index based on columns. So each of these columns has a header, a name, and then we can in fact add derived data of the sort that I've shown here. So for example, the raw data set has total number of hits, and then number of 2 base hits, a number of 3 base hits, a number of home runs or 4 base hits, but it doesn't actually contain the number of 1 base hits, singles, because that's all derivable. It's from this difference here. But if I wanted to actually add an extra column here that contained that information, I could just define a new column, the 1 base hits by this operation, and then on a row by row basis, it adds that data. I can aggregate data sort of in the same way that we saw with NumPy. I can, for example, say I want to know what the total number of each of these different batting statistics is over the entire data set. This would be the total number of each type of event over the entire history of baseball. That might or may not be useful. I can filter in various ways. I could, for example, ask, show me from the batting data frame just those entries where then somebody hit at least 60 home runs in a season, and that shows me this much smaller data frame here, which is gotten by filtering based on that Boolean condition. There's a lot of very powerful capability for what are called group by operations, and what these involve are a set of methods that allow us to support what are called split, apply, combine operations. So I can split a data frame into groups based upon some criterion, some key or something. I can apply some sort of aggregating function across each of the subgroups and then combine everything back into a single data frame. And this is very important because if you look back at what this, there's a lot of substructure within this. There are players who will appear repeatedly over different years. There are multiple players that appear in a given year, and we might want to try to develop some grouping statistics based on that. So for example, I can say if I wanted to group by the year information and then sum everything up, I could produce this new data frame, batting by year, which for each year sums over all the different players who played during that year, and then provides, in this case, a sum of each of these different batting events for each of the years in my data frame. So now I just have 152 rows instead of the many thousands I had before, because I'm basically summing over all the players. I might want to group by the players, however, and do a similar sort of sum. And so if I do that, now what I get is for the roughly 20,000 people who have played in Major League Baseball, I get their career statistics. This is the lifetime batting statistics by grouping over players and then summing those data. Pandas with these data frames, it's very easy to plot different things in various ways, and it's useful to know that Pandas uses matplotlib underneath, so that you can in fact interleave calls to Pandas plotting and matplotlib plotting, as I'll show you. So for example, I have this batting by year data frame that I created from the group by operation, and if I want to say, for example, plot the over time, what are the time history of strikeouts and home runs, I can do that, and it basically is using matplotlib underneath, so that and in fact, I can, if I wanted, I could come in here and I could customize this. I could say, I don't like the year ID. I want to call that X thing year instead. And so now I can interleave this call to matplotlib, which is then acting on this plot that was produced by Pandas. And so they kind of work, so often you sort of will do that kind of plot customization by using different packages. I can, if I want to look more closely at the relationship between home runs and strikeouts, I could make a scatter plot. This is just another sort of method on this data frame. And I can see that home runs and strikeouts tend to be highly correlated. And in fact, if I want to look at the correlation of all of the different event types in this data set, I can just, there's this other method which computes the Pearson correlation of all those things. And so, for example, I can go to home runs and strikeouts and see that they are in fact quite well correlated with a Pearson correlation of 0.96. If I wanted to plot some of this kind of stuff, some of this correlation data, maybe for just a subset of the statistics, I can essentially compute that correlation and then pass that through matplotlib to make a heat map visualization of the correlation in that data frame. So again, all these pieces kind of work together in a pretty seamless fashion to enable you to sort of customize whatever kinds of analysis you want to do. There's this stats models package, which I mentioned before, which does various kinds of statistical modeling. If we're interested in actually getting a quantitative fit to this home run and strikeout data, we, for example, could do an ordinary least squares fit using stats models. That's sort of shown here. I have the X value, the X data is our home runs, the Y data are the strikeouts. I want to, in this case, I also want to estimate the coefficient, the y-intercept. So that's sort of done here. And then I get basically a set of regression results and statistics that I won't go through, but which is a similar kind of thing if you have experience in R or maybe even in SAS or other kinds of statistical modeling environments, you kind of get reports like this. And in fact, the key thing here is that I get both a slope and an intercept along with errors in those things. And if I wanted, I could plot that fit. And in fact, in the same way that Pandas uses matplotlib underneath, so does stats models. Stats models has its own plotting API where now I can plot not just the data, but also the model results, this fit that I did. And we see the red line is then the fit to the data that stats models did through this ordinary least squares fit. And in fact, I can, in the same way that I did with Pandas, I can customize what that plot looks like using matplotlib commands. I was showing you reading CSV files, but you can also, for example, read Excel files. This is some data on California wildfires that we address in one of our CVW topics of Python for data science. And of course, in a Excel spreadsheet, you might not just have one table, you can have multiple tables on different worksheets. And so optionally, I can say I want to read in this case, data up through the year 2016 in this data set. And this then goes off and it parses this Excel spreadsheet. And what this data frame consists of is data on historical wildfires in California, 11,795 fires dating back to 1878. And one of the key elements here, for example, is this column GIS acres. How many acres did that fire burn based upon estimates from GIS, from Geographic Information Systems calculations? So I could do, just in the same way I did before, I could do, for example, some group by operations here, and I could plot as a function of year, what's the total amount of acreage that burned due to these wildfires. And we can see, as is perhaps not surprising, that's been increasing over time. We're getting bigger and bigger fires, more acreage burning. So that's sort of using Pandas in conjunction with Excel, with data that lives in an Excel spreadsheet. Some of you have been asking about a recent announcement by Microsoft of sort of the inverse of that, what's being called, I guess, Python and Excel. So instead of bringing Excel data into Python, there's this new product that Microsoft is rolling out that allows you to bring Python programming into Excel. And so this was recently announced by Microsoft and is sort of available through their kind of beta channel and at present only on Windows. But it seems like the plan is to kind of roll this out for all their platforms that they support Excel on. And what this does is essentially allow for execution of Python code within cells in Excel spreadsheets and workbooks. And that's kind of displayed here in these images. So this, if you can read on the left here, essentially, I can specify a set of rows and columns in an Excel spreadsheet and create a data frame from that. And then I could, for example, do one of these group by operations. I can say I want to group by category and compute the mean over each of those things. And this is similar to what I showed you. And on the right, there are some plots of some of that data using Seaborn, which is another plotting package that I haven't had a chance to talk to you about. but which, so essentially instead of, I kind of see this as instead of, say, using a Jupyter notebook to organize, your data and computations, you could, if you prefer working in Excel, this might be a useful thing. One technical point is that, as far as I can tell, so I've not used this myself, but Excel, you would run the Excel program locally like you normally would, but anytime you make a call to some Python code, it actually gets pushed off to the cloud to big virtual machines in the Microsoft Azure cloud that have this big Anaconda Python distribution installed. So every time you want to do one of these calculations, it's actually going off, into the cloud and doing some computation and then returning data back to your notebook locally. So that might or might not be something that you want to look further at if you like doing things in Excel. I tend to like to get data out of Excel so that I can do things with it in Python, but I realize that not everybody sort of operates in that way. So I hope I've given you some sense of sort of at least what some of these tools look like and kind of how they fit together. Again, I talked some about both the Python programming language and the Python C API, where if we write these extension modules such as NumPy that are actually able to run compile code using this API, then we can get much better performance if we structure our code appropriately to leverage that. NumPy, again, is really kind of foundational. SciPy uses it as kind of both SciPy and Pandas kind of use it as it really is sort of the substrate for a lot of any kind of array-based computation. We'll typically use NumPy underneath. I showed you a little bit about how stats models works in conjunction with that. Matplotlib gets used, and I mentioned both Seaborn and Pandas, and that use Matplotlib. All the plots that I've been making in this Jupyter notebook, I've been using Matplotlib, and we can render those within cells in our notebook, and so that provides a very nice environment for not just having code, but having code and documentation and results, and using notebooks to build narratives of data and of analyses and results and things. So I've provided this kind of overview of the Python ecosystem and showed you some of the functionality there. Hopefully giving you some sense. I mean, you may want to be using some of these other kinds of packages. If you're working with network data, NetworkX is a very nice package that lets you build representation of networks. Or if you're doing image processing, scikit-image is very useful. And then of course there's a whole series of packages that implement various operations in machine learning, which I think tentatively I think we're going to have a talk in this series in the spring addressing some of those kinds of tools. So we're going to continue with the exercises, but I realize we're getting close to 10 o'clock and maybe not everyone's going to stay. I want to thank you all for attending, and please stick around if you want to either work on the exercises or just want to watch the rest of us work on the exercises. Please complete the survey once it's sent out, and you'll get links to this material sent to you. I did want to pause here to see if there are questions about the scientific content. The matplotlib inline. Sorry, I'm just trying to sort out. Is there something I need to add? I don't think the problem is I don't need to check back later. Okay, if you don't have matplotlib, right? I think right. You need to, in order to run these things, you need to have the packages installed, and there was that thing at the top of the notebook that you can check to see whether you have the right things installed. If people, yes, the recording will include the exercises. So we're going to continue on till about 10:30. You can see we're sort of the exercises are down below here. In fact, I would encourage you, even if you can't stick around or whatever, but if you're interested, there's several exercises that we can work through, which we won't have time to work through all of them. If you want to use this as an opportunity to sort of see how these things work in more detail, you can, I encourage you to work through those. If you're just kind of getting started with Python, I did include a few little exercises, just some basic kinds of things to reinforce what I talked about 4 weeks ago. But the solutions are all there too. We have a question here. Can we use Pandas to join two tables and use it like a data management tool? Yes, Pandas does. It supports lots of, you can join on keys or, sets of keys. I mean, and the syntax is at least similar to what you would sort of think of in kind of a SQL setting. I mean, there are merges and joins and a notion of doing inner joins versus outer joins and so on and so forth. So I'm just want to see our poll numbers here. 30%. I have the tools and I want to do the exercises. 17%. I would like to do them, but I don't have the right environment set up. 43%. I'm not going to do them, but I want to stick around and a few others. So I don't know if I'm supposed to click share results. Is that? I don't know what that means. I'll share results. Maybe that shares that to everybody. I see. I was reading that. Right. So okay. Unless there are more questions by those who need to leave quickly, then I guess I will sort of move on to some of these exercises. And you can see in Jupyter Lab here, I've opened up the table of contents so we can just kind of see what we have here. I mean, there's a and I guess I was thinking, we would sort of maybe work through the first couple of these, but we can see how quickly that goes. Again, hopefully we can work through at least a couple of them, but maybe you're bored by some of them and you want to jump ahead, or maybe you want to work on them afterwards. So why don't we get started with that? So the first of these exercises is something that's often sort of taught in kind of numerical computing, and it describes the use of Monte Carlo techniques, Monte Carlo simulation, to estimate something. And in this particular example, is to estimate the numerical value of pi, which is approximately 3.14159. By essentially leveraging the role that pi plays in describing the geometry of a circle. So if we think about a circle, and I've got a circle here of some radius, a circle of radius r has area pi r squared, and the square that encloses that circle has sides of length 2r, and therefore has an area of 4r squared. And so if we ask what is the ratio of the circle to the the square that encloses it, it's basically pi over 4. And so pi is then equal to 4 times the area of the circle divided by the area of the square. And this is independent of r since it cancels out, but in the code below, we'll just assume r is 1. And we can estimate pi by generating lots of uniformly random points in the square, and then count how many of them fall within the circle. And then so that's what's being plotted here. I have lots of random, you could imagine me trying to throw darts at a dartboard, but I'm not a very good dart thrower. And so some of the darts that I throw don't even hit the dartboard, they hit the wall behind the dartboard, but some fraction of them do hit the dartboard, and that fraction, AC over AS multiplied by 4 will give us an estimate of pi. And so in this exercise, so what I've done is I've written some instructions here for what you need to write, and then there's basically 3 functions that I want you to try to write. The first of which will generate random points in the square. If I say I want n points in this square, you want to write a function, and you want to use NumPy, the NumPy np random.random function, to generate those points. We want to generate n points in the square. So we basically want to create an array that's got shape n comma 2, where the 2 refers to the x and the y coordinates of each of those points. Once you've written that function, then you want to have another function that takes in the set of points that are returned by that, which I'm calling p, and returns an array of bools of trues or falses, depending on whether or not those points are within the unit circle or lie outside of the unit circle. And then once you've done that, you can estimate pi just by essentially what Monte Carlo does is estimate these areas by the number of points the number of uniform random points that are falling within each of those objects. So if you've got the notebook set up and you've got things installed, you could start going in here. So I right now I have kind of dummy function bodies that just return the word pass, but I could start, for example, writing some code to implement each of these three functions. And I'll sort of pause for those of you who are working on this to try writing some of that code. If you have questions, please put them in the chat. I've done a lot of hands-on Python training, but never in a purely virtual setting like this. So any feedback as to what the best mechanism to try to support this. If it's easier to unmute yourself and ask a question, please feel free to do so. Rather than typing it in, we don't have such a big crowd here that wouldn't work. So I'll give you a couple minutes here. If you have questions, you can ask. I can try to provide some feedback, and then we can sort of jump ahead to the solution and see how what that looks like. One of the points that I made here is that, as I've noted, np.random.random generates uniform random numbers on the interval 0 to 1, but what we actually need to do here is create numbers from -1 to 1, and so you're going to need to multiply and shift accordingly to support that. If anybody has a solution and wants to cut and paste it, you could do that in the chat, or if you have questions. I know I'm going to want to return an array. I know it's going to involve something like a np.random.random n, 2, but that's not right, because that's just going to give me stuff in the unit in the unit square, or not the unit square, from 0 to 1, 0 to 1, not from -1 to 1. And then once I have those points, then I'm going to want to decide whether or not the distance. So essentially, the distance, whether or not something is within the unit circle, is whether the distance from the origin at 0, 0 to some point x, y, whether that distance is less than 1 or greater than 1, right? And so there's going to be but I don't want to write a loop over each of the points. I want to do it for all of them at once. So I'm going to want to return something. I'm going to want to access both the x and the y coordinates. And I'm going to want to compute a distance from them. How do I compute the distance from the origin to some point x, y? Are people making progress? A thumbs up if you're making progress. A thumbs down. Do they give a thumbs down thing if you're getting stuck? And then, as I point out, once you've written these functions, then you can sort of try to estimate pi with some large number of points. Written here so far is incomplete because this in-unit circle again is ultimately going to return an array of bools, trues or falses. So I'm going to want to do some logical operation to compare. I might want to calculate, for example, the distance to each of the points. actually compute a distance. I might need to, here's a hint I guess I didn't mention. If you want to take a square root of something in NumPy, that's np.sqrt. This is still incomplete though, because I haven't done the Boolean comparison. Okay, well, I'm going to jump, unless people say, no, I want to keep working on this. I was going to jump down to the solution and we can kind of talk through this and we can see what that looks like. So here are the three functions that we needed to write. So this first one, get random points in square. We want to generate n random points. I can return this thing. So, and what this is doing is, again, it's taking n random, pairs of numbers, x, y coordinates, which are on the unit interval 0 to 1. In order to get it from -1 to 1, I need to expand that interval. So I need to multiply it by 2. Now that's giving me uniform random numbers from 0 to 2. But what I need it to be on is from -1 to 1. So I can subtract 1 to shift that interval back. So I take the 0 to 1, I expand it, and then I shift it back. And that's what this is doing. And in fact, if I were to if we were to run this, you would get back that set of points, and you could verify that the maximum is going to be somewhere close to 1, the minimum is going to be somewhere close to -1 in along each of the axes. Then I have this function in unit circle, which takes all of the stuff that's generated by these n random points, and it computes the distance from the origin to the point x, y. And so it's the distance is the square root of x squared plus y squared, and then I want to check that this is less than or equal to 1. And so this will then return a true if a point in that collection, in that array, is within the circle, and false if not. And then to estimate pi, I basically get a bunch of random points in the square, or in the space. I compute the number of points that are in the circle, and I can do that by virtue of the fact that this thing in unit circle points is going to return a bunch of trues and falses, and if I sum those up, basically true evaluates to 1. So summing that array of Boolean variables will tell me how many of those are true, and so that tells me the number that are in the circle. And then the estimate for pi is just the number of the number that are in the circle divided by the total number of points times 4. And if I run this, I get some estimate, 3.14196, which is close to the real value of pi. If I do it again, I get some different estimate because it's a random estimate. As I mentioned up above here, what you really want to be able to do ultimately is get good statistics by simulating a very large number of points. But if you were actually to pass in an even larger number of points, a larger integer to this function, it would both take a long time, but it would also use up a lot of memory, because it's basically generating this massively large random array, which then it has to do, to compute on. But in reality, we don't actually need that array together. I mean, the random numbers are independent of each other. So we could, in principle, just generate a random point at a time and build up statistics, but then we wouldn't benefit from those vectorized array operations that I was describing to you earlier in the talk. So really a better way to do this is to sort of generate blocks of intermediate sized arrays, and then sort of so that you're getting the performance of the vectorization, but then you can sort of do that repeatedly to build up good statistics. And in fact, in our sorry, can I do that? If I click, and we have an exercise in our Cornell Virtual Workshop that in fact does this and sort of describes this kind of blocking strategy. And one of the things we can do is then look at how, for example, as n increases, our estimate of pi both converges to the actual value, and that the uncertainty in that estimate also decreases, which is sort of characteristic of Monte Carlo. I guess we'll move on now from this exercise, but I did want to at least sort of describe some of those some of those nuances there. If you're interested, you could try to figure out how to make a plot like the one I was showing you with the red and the blue points. And you could also, for example, look at the performance speed up of using these vectorized operations, then doing it all with endpoints at once versus the solution where you would generate one random number at a time, and then build up statistics that way. Hopefully some of you got at least partway through that, but if not, again, I encourage you to sort of go back and work through, and in fact, you can, each of these steps along the way, you should sort of test them. I mean, we could in fact do that here. We could go down to our solution. Where's our solution? There's our solution. And we could, for example, add a new cell, and I could say, if I just wanted to say, what does get random points in square of 10 look like? I just want to generate 10 points. Sorry, I need to P. Then again, I have this n by 2 array where each point has an xy coordinate somewhere in that square. And so you could test each of these along the way to see that it's doing what you want. Here's a second exercise, getting back to baseball statistics and sort of involving the issue of kind of parameter estimation. And this is sort of goes back to some of the early days of kind of more advanced what are called sabermetric statistics in baseball. So this is not about batting, but about team statistics. In order to win a baseball game, a team needs to score more runs than its opponents. And over the course of many games, the relationship between the total number of runs scored, the total number of runs allowed, and the game's won gets murkier, since a team might win games by a little bit, but lose by a lot. And so Bill James, this famous statistician asked, what fraction of games does a team win based on how many total runs it scores and how many total runs it allows to its opponents? And he postulated this relationship, that the fraction of games won, so W over G is the fraction of games that a team wins, say, over the course of a season, as this relationship involving the number of teams that number of runs that the team scores and the number of runs that they allow. And this has been dubbed the Pythagorean theorem of baseball, because we kind of have things that are sums of squares, and that looks like the Pythagorean theorem that we study in geometry. But when people have actually looked at so James originally postulated this, but then when people have looked at the actual data over the history of baseball, they've suggested that it's better explained by some exponent that is different than 2. So some other exponent P that's not necessarily equal to 2. And so let's try to estimate that exponent P by fitting the model to the data. And if you want to see more about this problem in detail, you can go off to our CBW page where I talk about that. So there's a few steps here. The first step, you can just execute this code cell here. This is just reading in, not we read in before the teams database, but now we can read in we read in the batting database. Now we can read in the teams database. And I'm doing a little bit of filtering. I'm actually just looking at the teams that played at or after 1900, since the very early days of baseball had different rules and the statistics are a bit different. And then I created, as I showed you before, I created some new columns in this data frame, which I'm now calling team 00, which are this win ratio, W over G, and the runs allowed over runs ratio. And then I can make a scatter plot similar to what we looked at before. So this is this relationship that James postulated between W over G and RA over R. And what we're basically going to want to do is try to estimate what exponent in this relationship here best fits that data. And so what we're going to use is a different function from the SciPy .optimize package called curve fit. And so, for example, I can uncomment this thing, and we can look at the documentation for curve fit. And what we can see is that it uses nonlinear least squares to fit some function f to data, and the data are provided as x data and y data. And so essentially what it wants to do is it wants to find the set of parameters that best fits f of x to y. And then there's lots of other options that are sort of provided. I suggest you could look at that in the notebook and then maybe rerun the cell by commenting it out so you're not seeing all that documentation. But essentially what we need to do, in the same way that we looked at before, we need to write some function f that summarizes the problem we're trying to solve, and then we have our data, which are in this data frame here. So what the exercise consists of is now so I want you to write a function that basically, which I'm saying you could call it something like Pythag for Pythagorean, which takes x data, x, and a parameter p, which in this case is this exponent, and will return the model. We're fitting the data to a model. This equation here is the model. So you want to write a function that returns for x and p that the application of that function using those parameters. And I should say, if we look at the curve fit documentation again, the p is actually in principle, you could have a model with multiple parameters, such as we had with the SIRS infection data. So even though we have a single parameter here, you'll want to treat it as if it's as if it's an array. So you first want to write this function, and then you want to call curve fit to find what the optimal parameter set is, the p opt. So why don't you start working on that, and then once you have that, then you could, for example, make a plot of the data, and then they're going to be sort of you could compute, for example, if p were equal to 2, what would the expected number of wins be? If p is equal to whatever the optimal value is that gets returned by this curve fit, you could plot that, and we'll look at that once we get to the solution there. And if you have questions, please put them in the chat. There was a question here, right? So Christopher wrote, he didn't think that pandas will merge the tables in your actual, you would, if you were doing database-like operations within pandas, you would be doing those within pandas. You could merge two data frames and create another data frame. If you wanted to then write that merge thing back to a database, then you would need to, as Christopher pointed out, there are other packages such as SQL Alchemy, which is something that I've used that connect to a SQL database. It could either be something locally on your machine or something out on the internet, in a database server, and then you can essentially read and write data frames to that database using pandas. That's one mechanism. Again, I'm writing a function here at Pythag, so I want to return some value. The x value, the x data is just RA over R. That's my x data, that ratio. And the y, and then the y data are this. So I want to sort of write something that captures this relationship here. Of course, you want to make sure when you're doing division, you want to use grouping operations, parentheses, to group things. There was an interesting story in the New York Times a few months ago about how certain kinds of arithmetic problems are sort of, when posed as natural language, are sort of sufficiently imprecise that there are different ways of writing, of actually computing those things that was what was sort of being debated in the article, which was interesting. But that's a digression. We've imported curve fit, so we're going to want to do something like curve fit, and curve fit takes a function f, which is our Pythag function, and it's got x data and y data. Pythag, not Python. The x data are in our data frames here. In our data frame, that's the y data, isn't it? Well, I'm going to do that. Oh, jumping too far ahead. If you have questions, please let us know. Well, why don't we jump down to the solution and have a quick look at that. So we read in the data, we imported curve fit. So this Pythagorean, the model that we're fitting to says that y is equal to 1 over 1 plus x to the p. So that's the function that we want to do curve fit with. And we want to call curve fit with the function with the x data and the y data. So if we run all this stuff, we get our plot, we get our import, we define our function, and now we print popt. So popt is it's an array with one value in it, the parameter 1.8376. So instead of providing an optimal exponent of 2, like was originally hypothesized, this fit here suggests a little bit less than that. It's 1.83. If you go to the baseballreference.com website, they claim it's 1.84, but they don't actually tell you how they've computed it. So I don't. It's hard to know what to do with that. And in fact, if you go back to this thing that I linked here, there's actually a very nice. So we implement this. Oh, right, we'll do this plot in a moment. But in fact, there's sort of a very nice post that is available online that sort of explains why, what the role of these kind of nonlinear fits and what different terms. There are actually lots of competing models that have been proposed that are slightly different, that have higher order terms. And Ben Vollmeyer-Lee has done a really nice job of kind of explaining the underlying mathematics of that. But now that I've computed this thing, right, so now I want to, excuse me, I've been talking for a while. I can, for example, I can plot the data that we have. I can plot the value of f given the value p equal 2, and I can plot the value of f given the value popt of 0. So popt is an array of length 1, so popt 0 is this value 1.837, and so you can see that the two models are not so different from each other, but at least from the point of view of a least squares fit of the model to the data, the value of 1.837 does a slightly better job than fitting the data than the original estimate of 2. And so again, this is an example where we might have some model, we might have some data, we want to estimate parameters. The whole field of parameter estimation is a big complicated thing that has many subtleties, but a lot of that sort of uses these basic kind of tools of doing some optimization. If you're for example working with neural networks and you're trying to train a neural network on some data, essentially the same kind of thing is going on. There are lots of parameters that the neural network has internally with edge weights and biases and the like, and what it does is iteratively refine those estimates of those parameters to provide a better and better description that, for example, maps a set of inputs to a set of outputs. I mean, so the same kinds of optimization techniques are going on under the covers in some big package that supports training with neural networks as we're sort of doing here. But often, you for a given problem, you might end up having to write this kind of code yourself. We're getting close to the end of the session here, so I just wanted to sort of quickly go show you a few other things here. I mean, you can work through these, but for example, with our infection model, I mentioned that these things reach steady states where we have some endemic level of infection and other variables. And in fact, we can solve for those steady state values without actually doing this time integration by doing essentially root finding. And so this third exercise here is basically showing you, walking you through how to use a root finding function from SciPy to compute what these steady state values would be without having to actually do this time integration. There's another example where we solve a different set of differential equations, the Lorentz equations, which are famous in the history of dynamical systems theory. These are a set of equations in 3 variables, and you may have seen this famous picture of the Lorentz attractor, which is a chaotic attractor. In this part of parameter space, the dynamics is chaotic, and so it never settles down. It just but it does fill out this complicated attractor. Although, for example, if you change one of the parameter values and remake the plot, you find that in some parts of parameter space it actually is stable, and so some initial trajectory will, for example, spiral into some stable fixed point. And somewhere between this value of s = 4 and s = 10, which leads to this chaotic thing, there's some bifurcation where this stable fixed point becomes unstable and eventually gives way to this chaotic attractor. And this is the kind of thing that you can study using these kind of tools. And then the last exercise is another one of these things, sort of trying to figure out how to do some slightly more complicated kind of computation rather than writing something out explicitly with for loops, figuring out how to do that using array operations, in this case to compute a Laplacian, which is a sort of a differential operator on a field. And in the same way that we did some timing stuff before, we can see, for example, that to compute this Laplacian on this 1,000 by 1,000 array, I can speed up from 735 milliseconds to 6.04 milliseconds by using the right kind of array operations. So unless I guess we're 10:30 now. We should sign off if anybody has additional questions, please post them in the chat right now. I encourage you to, again, if you want to work through these, please do so. If you have questions about it, please reach out to me by email. I'd be happy to discuss, any of the stuff in this notebook here. And thank you all for attending. As I say at the very end, the very last thing, right? So if you run the entire notebook to completion, you can see that you've got everything working correctly because you reached the end. So